Hello everyone. Today we will see how to analyze the protein secondary structure from FTIR data in OriginPro software. So, so first of all, we will see the levels of protein structure. So we know that under physiological conditions at a distinct pH, a polypeptide chain will not uh, be in a linear extended conformation, but it folds and it forms a more compact shape, usually consisting of several layers. So the local folding arrangement of this polypeptide chain is known as the secondary structure. So for example, here we can see this is an example of hemoglobin. This is a protein. So in the primary structure, we can see there is a sequence of just amino acids. This is glutamine, serine, phenylalanine, and glycine aspartic. So this is just a representation of the sequence of amino acids. Now this is the secondary structure that we are mostly focused on and to estimate the secondary structure using FTIR data. So this secondary structure is the localized conformation of the polypeptide backbone and it looks like this, and it has different representations like alpha helix, beta sheet that we will discuss in the next slides. So the next structure that is most commonly represented is the tertiary structure, which is a three-dimension structure of an entire polypeptide chain, including all its side chains. And also the quaternary structure is the special arrangement of the polypeptide chain in a protein with multiple subunits. For example, this is the subunit, and this gray colored is a different subunit, and this is a arrangement of different subunits, like the multiple subunits. So this was the example that I have taken from this source. Now if we go much deeper into the protein secondary structure, so it describes the local folding pattern of the protein backbone, that is how it folds and what is the pattern of folding. So in FTIR, when we do the FTIR, the amide band 1700 to 1600 centimeter inverse, which is the wave number, or the which is called the wave number, is commonly used, and we generally use this wave number range because it mainly associated with the peptide CO stretching vibration. So CO stretching vibration, this is mainly we are focusing on. So if we do the FTIR analysis, we generally do from 4000 wave number to 400. But for the protein secondary structure analysis, we generally focus our range on between 1700 to 1600, and whatever peaks comes in between this range, we calculate the protein structure, secondary structure. So after when we get the FTR analysis, we do the deconvolution or the fitting of this region, which is the 1700 to 1600 of number, and which allows the estimation of beta sheet, random coil, alpha helix, and beta turn associated components. So we will identify the percentage of each of these: beta sheet percent, random coil, alpha helix, beta turn, and these relative components can help indicate whether whatever treatment we are giving to the samples we are causing some unfolding or ordering or aggregation or any local conformation rearrangement in the protein sample. So in this figure we can see this is beta sheet, which looks like a sheet or a folded sheet, and alpha helix is a helix pattern like this, and random coil is it folds like a coil which is random. So these are the different percentages that we will calculate: the percentage of alpha helix, percentage of random coil, percentage of beta sheet afterwards. And this is another figure in which the alpha helix is shown here, random coil is shown here, and the beta strands and beta turns are shown here. Now the secondary structure in their FTIR amide 1 region we are focusing on, which is the 1700 to 1600, as we already discussed. So generally the amide bands are broad because the several protein backbone conformation absorb in this region. So what we do the deconvolution process. What this process does, it separates the overlapping band into its component peaks. So for example, look at this figure. So this is a FTIR amide 1 band, this black band. So this we can see it is a broad peak. So we cannot identify what individual components are. So what we do the deconvolution. So it separates into individual components. For example, the beta sheet is there, alpha helix can be identified, random coil, beta sheet. So all these can be done with the help of deconvolution. And then we calculate the relative area of each of the fitted component, and then it is used to estimate the contribution of secondary structure. So for example, if we calculate the beta sheet percent, it is total beta sheet peak area divided by total fitted area into 100. So for example, this is the beta sheet area, and the total area is the sum of all this 1, 2, 3, 4, 5, all the area by total area into 100. So this is the beta sheet percent. And this figure shows the wave number which is from 1700 to 1600, and these are the different components that I have already discussed in the right hand side image. And here the table shows, sorry, so this is a table which is showing beta sheet, which means the extended sheet like ordered structure, often linked with aggregation, networking. Random coil is linked with more disordered nature or flexible protein backbone. And these are the wave numbers that are specific wave numbers. And if any peak is coming between this wave number, so it must be a beta sheet. If any peak is coming between these wave numbers, it must be a random coil. Similarly, alpha helix is there, which represents a compact spiral shaped or ordered structure. Beta turn is short bending region where protein changes direction, and high frequency beta sheet is also there in the range of 1682 to 1700. So these are anti-parallel beta sheet associated components. Now let us see the equipment that I will use in this video to calculate the FTIR assisted secondary structure. So I will use this equipment, FTIR UATR PerkinElmer spectrum tool. So this is the equipment as you can see here, and this is a holder or that we first slide and we put the sample here, and then we again put it the slider here and we rotate it clockwise to press it. That I will show everything step by step, and then we go to the monitor to check the peaks. So here we can see here the Fourier transform infrared spectroscopy or FTIR is used to identify molecular functional groups by measuring how a sample absorbs the infrared radiation at different wave number. So for example, if we are doing between 4000 to 400 centimeter inverse wave number, so the FTIR will measure how the sample, for example, I have any sample I have kept here, how it absorbs the IR radiation, and similarly it will give the different peaks at different wave numbers. So this is the main concept of FTIR. And what does UATR means? UATR means the universal attenuated total reflectance, and it is an external accessory that is fitted to the FTIR equipment, and it includes a diamond accessory which allows direct measurement of solid or liquid samples with minimum preparation. We have to put the sample and press it, and then it will give the reading. And in ETR FTIR, the sample is placed against a highly refractive index crystal, and the crystal you can see here it is. I will show you there also in the next slide, and which mainly is diamond. And infrared light reflects inside the crystal and creates a small wave which is called evanescent wave that penetrates only a short distance into the sample surface. And molecules in the sample then absorb the IR frequency and then producing the FTIR spectrum on the desktop. So first what we will do, we will check the protein powdered sample, and it must be dry, and we will first check the moisture also. It should be within the range, and we will press onto the diamond UATR crystal, and the infrared beam will reflect inside the crystal, and the Evanescent wave interacts with the sample surface, sample absorb the specific higher frequency, and then we will plot the wave number versus absorbance. And different peaks will come like this, and then we will separate between 1700 to 1600 for our secondary structure. Okay, so this is the video that I want to show you. So first let's play this video. So this is the equipment. This first we will you rotate this. First we will see how it happens. We will remove this cover, and this is the crystal you can see here, and this is the crystal you can see. And then these are the desktop that is connected to it, and this is the software Spectrum IR that you have to open, and you have to use your login credentials in the software. Okay, now we have to now let's see how to use the sample. So first we will put the sample here. Very little sample we have to put just to cover the surface, and then we will start rotating it, but we will not rotate it fully. And now here we will open file, and then we'll go to new sample, and we will change the sample name in the sample ID. For example, let's see, we change the name to 44 R2, and then we are setting 32 scans here, 32 scans in the accumulation, and the wave number we are selecting 4000 to 400. Now we will go to measurement and scan. So here we are seeing the force gauge. So first we will rotate a little bit clockwise, and then the force gauge percentage will increase. So our target should be 75% of force gauge percentage. So we will rotate the knob until the force gauge will reach 75%. So currently it is 39%. So we'll rotate more in the clockwise direction, and then we can see here it is reached 75%, 75, not percentage. Now we will go to measurement again, and then we will scan again, and now it will scan in percentages. So it is currently 0%, and it will now scan, and it will reach up to 100%. So we have to wait until it reaches the 100%. And you can see here now it is 12%. Now we'll fast forward a little bit, and now we can see here it is moving 93, 96. Now it is 100%. So now the sample is scanned completely. Now what we'll do, we will go to process, and we'll convert into absorbance. Currently it is in transmittance, so we will convert into absorbance. So now we can see it has converted into an absorbance graph, and then we will do the ATR correction. So ATR correction will go, and this is the ATR corrected graph that we have obtained. Now we will go to export, and then we will save this as a CSV file or Excel file, and this file we will use in the OriginPro. So now let's go to OriginPro to calculate this. So first we will go to, this is our OriginPro software, and we'll first go to file and import and single ASCII. Then It was a 44 number sample, so I will select the 44, which is a CSV file. You can see here, this is already converted into absorbance and already converted into already ATR corrected. Now we will open this file. So here we can see it is open and it is starts from 4000 and it ends with 400 because we scanned from 4000 to 400. Now we will select these two columns and go to worksheet and then press the worksheet query, and we will write a query to separate the wave number or to select a range only between 1700 to 1600. So for that we will write this query col1 col1, which is the column 1, which is AX, and it should be greater than or equal to 1600, and ampersand sign shows that both the left hand side and right hand side of the ampersand sign must be true. Then the answer will be true. Otherwise, if any one of them is false, then the answer is false. Col1 should be less than or equal to 1700. So this is the query. Col1 is just AX, and now we will extract to a new worksheet, apply, close. So now we can see here it starts from 1700 and it closes at 1600. And why we are doing this? Because we want the amide 1 region for calculation of the secondary structure, and amide 1 region generally starts from 1700 wave number to 1600 centimeter inverse. Now what we will do, we have got this. Now we will select this. We have already set as this is the y. We already know this is y. This is already set as x. Now we will select this y axis and we will go for a smoothing process. So what we will go in signal processing, smoothing, open dialog. Now here this dialog box will open, and what we will do, we will select the point of window as 7 because the more point of window it is better in some cases. And the polynomial order will select 2 and just leave it all like this, and then we will select OK. So here you can see this is the smoothened graph y-axis, and the x-axis will remain the same. Now we will select the x-axis and press the control button, and by pressing the control button, do not leave the control button in the keyboard, just press this. Now leave the control key and then go to here and plot a line graph. So this is the line graph, but here one problem is that this is just the both ends are not equal, at not equal height. So what we have to do, we have to do the baseline correction. So we will do the baseline correction here. So what we will do, we will go to analysis, peaks and baseline, peak analyzer, open dialog, and we will do subtract baseline. Here we'll click subtract baseline, then we'll go to next. We will select here user defined, we'll select, and currently we'll see there are 3 points coming. So what we will do, first number of points to find, we will select from 8 to 2 and we'll select find. So currently it is not coming on the edges, it should come on the edges. So let's see, we'll put it 2 here. Now see, now it is on the edges. So the 2 points are in the edges. Now we will go to next and we'll select this spline method of interpolation, and then we will go to next and we will press the subtract button. So now it comes, it is subtracted, and the baseline is equal. Now we will go to finish. So this is the older version. We will go to the curve, and these two are the subtracted. The subtracted, this is already smoothened, that we did the smoothing process. Now we have subtracted the baseline. So this, from now onwards, we have to work on these two x and y axis data. So we will select both of these, and then again we will plot the curve. So now we can see the edges. We can see the edges are at the same y-axis, at the same y coordinate. Now we will select this graph. A rectangle box will come like this. Now what we have to do, we have to go to analysis, peaks and baseline, and then we have to go to multiple peak fit, and then we have to open a open dialog. Now we have to do some changes here. This is the peak function. We will want to change to Gaussian. Remember, do not change to Gauss amp or Gauss. You have to choose the Gaussian. Gaussian is selected, and now we will go to OK. Now here it is showing that double click to pick peaks or single click to move, single click and move left and right arrows. So this is a plus sign that is coming. So we have to select at least 5 or 6 peaks, and I am selecting on the basis of previous trials, because in plant protein samples generally we have selected 5 peaks, as we can see here in this slide. We can see here these 5 peaks we will select. For example, peak 1 1620 we will select, peak 2 1632, peak 3 1642, 1654 is peak 5, peak 4, and peak 5 is 1670, peak 6 is 1688. So we'll select on this OriginPro. So let's select one by one, and I will show you how to do that. So first select 1620. So 1620 will come, just it is here. So first we will press randomly. So in the green color is showing 1618. So we will move a little bit upstairs, up, and now it is 1620. Now we'll press a double click. So it shows that we have picked one peak. Now we'll go to 1632. 1632, it is now 1632. We'll select quickly. Yeah, we can go random here, and later we can select the exact number in the table that will be made. Now double click I have done, and now for 1642 we'll do, here it is 39, 1642 it is here. So we'll present, double click here, and then 1654. 1654 we can do here, and 1670. 1670 I have selected. Now the last one is 1688. 1688 will come somewhere here. 1693, 1688. Yeah, so I have now selected, it is showing that you have selected 6 peaks here. So now I'll go to open NL fit. So this dialog box will open now, and now I have to do the main thing, which is the setting. So this is the parameter tab, this is the bound tab. First we will select the parameters. So here we can see the parameter tab exact settings what we have to do. So here the y node we have to put the value 0, and it should be fixed. So y0 is the y-axis, so we will put it fixed, and value is already 0. Now here the xc values, xc 1620, and the fixed, it should be fixed. So xc, it is here, it should be 1620 exact. So I will put the value in the value column, it will be 1620, and in the fixed column it should be fixed. Now area, xc2, first we will do the xc2. xc2 should also be fixed, and the value is 1632. xc3 is fixed, and the value is 1642. So that's why I was choosing in randomly just approx values, because here we can change the value to an exact value that we want. xc4 we will select 1654, and xc5 is also fixed, and all the xc values are fixed, and the value is for xc5 is 1670, and for axis 6 the value is 1688 and it is also fixed. Now what we have to do, all the area values and the width value of the peak should not be fixed. So that's why the area value I have not fixed. The width is also not fixed here. Similarly, the area 2 value of area 2 means the second peak. The area of the second peak is not fixed. The width of the second peak is also not fixed. Similarly, for area number 3 and width 3, area 4 width 4, and area 5 width 5. These are not fixed. Now we'll go to the bounds tab. Now the bounds tab is very important. We have to do this carefully. So why the bounds tab is done? Because it prevents the unphysical fitting. So bounds keep the fit chameleon mathematically reasonable. So what we have to do, the area we have to all the areas should be more than or equal to 0 because the area cannot be negative. So what we will do first, this is the area. So first we will press this, click on this A, and then we will go here and double click here. So when we'll double click, the symbol of greater than or equal to will come. Now we'll double click this, two hyphens are there. So when we'll double click, it will be active, and when we'll press 0. So now this area is area for the peak one I have set. Now anywhere, just right click here and apply the same bounds to all the A. All the A means the area for all the 5 or 6 peaks that we have to. So so when we will apply, so area 2 will also be greater than or equal to 0. Area 3, as we can see here, A3 is greater than, now it is set already. Now next, all the area should be greater than 0, and width we have to select between 5 to 35. So width we can select. So first we will click here, and it should be greater than or equal to, and here we will select 5, and here it should be less than or equal to sign, and it should be 35. So this FWHM is just the width only, so should not be confused. Now we'll click anywhere, and we want this range for all the W, all the width of all the 6 peaks. So we will apply the same bounds to all the W. So for W2 we got the same, and for W3 also we got the same, W5 we also got the same, W6 we also got the same. Now what we'll do, for center they are already fixed. So center, we can see the center, that is XC, we already fixed. So no, because since it is fixed, so we cannot put the bounds. So it is like this. Now it is all come done, and then we will press this fit button once. So what happens, let's see. Do you want to switch to the report sheet? So we'll go yes. So now we have got the detailed result. Now we'll go to the summary table, or before that we will see this. Before that we will see here, we can see the fit converged. It is saying that the total iteration it took was 23 iteration performed. R square is 0.999, which is very good. The fitting has been done properly, and the fit has been converged. The chi-square tolerance value was reached. And now we'll go to the fit status code. It is already showing 100, and fit is converged. We will copy this summary table, or before that we will see this curve. So delete this, and here we can see the all the individual deconvoluted peaks are here. There are 6 peaks, and this, the black cumulative fit peak and the subtracted, it should coincide, which shows that the fit has been done properly, and the individual component peaks have the area less than the total summation of the all the peaks, which is correct. So we will save this graph. So we can export this graph and open dialog. We can open dialog, and we can export this in PNG format. Anywhere we can save. And okay, now we'll go to the result sheet. So this is the result sheet. Now we will copy this, copy the table, and then we will go to Excel sheet. The Excel sheet I will provide in the description. And here it is already a formula that has been fixed here. So what we have to do, just we have to do like this, and we will copy this and paste it here. Okay, so when we will paste it, the values are shown here, and the beta sheet we can see here 38.97%, random coil is 21, alpha helix is 15, beta turn is 24. So how I did the calculation, so I will show you a little bit in the presentation. So first we ran the fit and we checked the convergence. A high square value, high R square value is not just enough, it should also fit, and the fit status should be succeeded, that is 100, and fit should be converged, and the chi-square tolerance value, it should show that it should reach up to a level. And if the fit is not converging, then you have to do it again. You have to check the bounds, you have to check the parameters, and you can change the parameters also. And the R square value should be more than 0.99 for a clean amide 1 fit. And the area value should also be positive. Check the width are inside the bounds and not always stuck at the boundary. Check cumulative fit visually follows the experimental curve. And this is a checklist that you can use. The fit status, adjusted R square, all area should be 0, and this I have discussed all. And now this is a formula. Okay, so the total area is the area of all the peaks A1, A2, A3, A4, A5, A6. So the total area that I can see here, it is the area of all the, it is the sum of all the areas. So these are the all the areas of all the 6 peaks. So the area, the sum is coming 1.16578, which is the same as here. So the total area we have calculated. Now the beta sheet percentage is, beta sheet is just this peak 1, A1 plus A2. So peak 1 plus peak 2 will give the beta sheet values, as I have already shown in the presentation. You can see here peak 1 and peak 2 will give the beta sheet. Peak 1 and peak 2 will give the beta sheet. Peak 3 will give random coil. Peak 4 will give the alpha helix. Peak 5 will give the beta turn, and peak 6 will also give the beta turn. So these two we will take the average for these peak 1 and peak 2. For beta sheet, for random coil we'll just take the A3. For alpha helix we just take the A4. We will take the average A1 plus A2 for beta sheet, and we'll take the average here, I think A5 plus A6. We'll check here. Yes, so for random coil we'll use A3 divided by total area. For alpha helix A4 divided by total area, or beta turn A5 plus AC divided by total area. So that's what I have done here. For beta turn, it is the area that is E7. Yeah, this one is the beta turn, which is the peak 5. And so I hope you have got the logic how I have calculated the area for all the beta turns. And now we can see how to interpret. So generally this is general interpretation, this is not universal. And higher beta sheet may indicate the increased ordered beta structure, aggregation, related organization, or a stronger intermolecular interaction. And higher random coil may be usually suggests the increased disorder, unfolding, or loss of ordered structure, whereas lower alpha helix can indicate unfolding or rearrangement of helical structure, whereas beta tone changes may reflect local chain bending, conformational, or rearrangements. So, so we do not interpret the tiny individual peaks, we interpret the group structures, and also we do not just come to a conclusion from the FTIR secondary structure data only. We generally establish a link between other tests also, between secondary structure data and other data for the protein, for example, solubility, hydrophobicity, STSPH, rheology, or microscopy to support the interpretation and to establish a link. Then only a proper analysis can be explained. So this is all about the OriginPro software. Now we will save this also as a project. So we will save project as, and we can save here. For example, I have saved all these files here, we can see. So now we'll save here as a project.opju file, and it will be saved here. So I think this is all about the FTIR analysis for secondary structure estimation, and I hope that you like the video. Thank you. So we have got the report sheet here, and this much effort is for one sample. So suppose if you have multiple samples, then it will be very tough job to do for all the samples. For example, if you have 20 samples, so for that there is an option called dialog theme. So we can save the theme and then we can use it without filling all the details again and again. So for that, go to this green lock, and this is green lock, and go to save theme as. Now what you do is save, you can save as your general name, for example, general FTIR theme, or maybe anything. And this is the important we have to select here. So for that, what we have to click, I will tell you. So click the function and selection, click auto parameter initialization status, parameter values, fixed status and fixed values. Untick this, and upper and lower bound is mandatory, and other settings it should be there. So I have saved a theme here, so I will just show you here like this. So save it like this, and you remember to click this or tick this options, function selection, and auto parameter initialization status, parameter values, fixed status and fixed values, upper and lower bounds, and other settings. Now click OK. So as I have already saved this as a theme, so it is saying file already exists, overwrite. So I will just overwrite. Okay, now I will show you example how we can do for the next sample. So suppose I will go a new project. I want to do earlier it was 44 number sample. Now I want to do a different sample, 45 suppose. So I will import the data for 45 number sample, and then I will do the same procedure that I did before. And worksheet query, I will write the query 1600, and so this is correct. Extract to a new worksheet, apply, close, and then I will do the smoothing process. I will go to analysis, signal and processing, and smoothing. Now one more thing is that you can do the open dialog, but it will take again a lot of time. So for the initial, in the first time if you're doing, you can do the open dialog, and it will automatically save in the last use, so you can use the last use. So this is also a time saver. So you can select both these, and then you plot the graph, and again you have to do the baseline correction. So for baseline correction, I will not recommend you to do the last use because sometimes it may not work. So for baseline correction, better you use open dialog box and subtract baseline. Next, user defined. Now you press it to here. Let's see if it is, again it is not coming on the edges, so use 2, smoothing window size, fine. Now it is coming on the edges, the red points. Now we'll go to next, spline method of interpolation. Next, subtract. Now the baseline has been subtracted, we can see, finish. So we'll go to the data and we will use these two columns. These are the subtracted, and before that it has been smoothened. Now this I will click once to get this rectangle box. Now I'll go to peaks and baseline, multiple peak fit, and I will open dialog. Then I will select the Gaussian, and then nothing to do here. Just press OK and open NL fit. Click once. Now here we have already saved the dialog theme, so just nothing to do here. Just go to this dialog theme and press on this triangle and use this theme. This was the saved theme, general FTIR secondary structure calculation from FTIR. So when we will click here, it will automatically feed all the values here. So no need for again and again filling it. It is just a waste of time. So again, the bounds are also filled here, what we have used. Now just press fit. It is saying that we want to switch to the report sheet. So we'll say yes. And again, we have to check which is very important, if it has converged or not. So fit convert, it is showing here fit status code 100. And now you will again copy the table. Again, you will go here, and then you will copy this and press here, paste it here. So you can see the beta sheet value, random coil, alpha helix, beta turn, everything is here. So this is just a very handy tool to use the dialog theme option, and you can use the dialog theme option for anything. For example, if you want to save this image and if you want to export the graph, so you have to again and again select this, again and again you have to select convert into PNG. So better what you do, you select the appropriate folder location, and then what you do, you save as a dialog theme, save as dialog theme whatever you write, graphs or anything, and you press OK. So then it will be very handy. So what when you will go, so when you will export and you will use, suppose I have saved this theme as FTIR fitted plot, so it will be automatically saved here, and when you will go for the fitted plots, so it will be saved in the file. So there is it will be saved like a PNG file, so there is no need to worry. So it is better to use the save theme, and for the first time you do the all the without the save theme, and then later to save the time you can use the save theme option. Thank you so much. I hope you like the video. Thank you so much.